So, you've designed and prototyped your electronics project, and you want to learn how to package it into a basic PCB. Well, this video will take you through that process, from drawing your circuit diagram to designing the physical PCB to fabricating it using a PCB manufacturer like PCBWay, the sponsor of this video, but more on them later. And finally, to assembling the PCB with the electronic components. At the end of the video, you'll see an example of PCB design for an object-avoiding robot. So here's the basic workflow of PCB design. First, we draw our circuit in something called a schematic. This is meant to show how the components should be electrically connected. This is different from a physical connection or placement of components, which is for the next part. Once you draw out your circuit, you can place things called footprints of your components. Footprints are essentially the holes or the metal pads that you'd connect your components to. These footprints are then connected with metal traces, basically wires, to other footprints, which is all based on the schematic you drew before. Once you're happy with the PCB design, you can send it in to a PCB manufacturing company like PCBWay to have it made. I like to use KiCAD to design my PCBs and circuits. It's free and it works well. By the way, I won't be covering how to download KiCAD, but you guys can search how to do it elsewhere. So let's get into the details here. We'll be using the LED and ultrasonic circuit with an Arduino as an example from the last video. So you've downloaded KiCAD and you've opened it up. So you could go up here to File and press New Project. And I'm just going to save it in the Documents in KiCAD folder. And I'm going to name this Tutorial PCB. And we're going to start with the schematic, which is where you connect everything together and lay out how everything is electrically coming together. And so we could go up here to add symbols and wait for it to load. Okay, so it's loaded in, and now we can put in an Arduino. So fortunately, KiCAD has saved a lot of things into its library. So we can actually search up an Arduino Nano schematic symbol, which is what it's called. And also it has a footprint. We'll see what that does later on. So I'm just going to use this one. The next thing that we want is an LED, simple LED symbol. And this is what an LED looks like in terms of a schematic symbol, which shows the direction of positive flow and these two arrows coming out showing light being emitted. LED stands for light emitting diode, so that's why there's that there. I'll worry about the ultrasonic sensor later. For now, let's try and connect stuff together. How do we power all of these things? Well, for one, we need a power supply, and then this LED needs to be powered by a pin as well. So I guess we could start with that. We could connect this LED to any one of these digital pins that we've seen before. I'm just going to use digital pin 5, why not? And there are multiple ways of doing what I'm about to do. So, oops. If I press R, I can rotate stuff and then click and drag just to move it around. We need a negative connection on this end so that the LED can have a complete path to have electricity flow through it. But commonly what you would see in more advanced schematics would be something like this. So you would connect this to ground, and then what does that ground mean? Well, it would also connect to this ground. So this is the same exact thing as before. This essentially makes a imaginary wire between grounds. And why would you want to do this when you could just connect it like that? So if you have a lot of components like this project here, my self-balancing robot, you can kind of imagine how many wires you would need to connect all of these grounds together, up here as well, and there, and there. It's going to make it very crowded. So let's get back here. And how we would power this is we would just connect the USB to it and we'd be fine. Now, the ultrasonic sensor, if you search up ultrasonic here, they're not going to have the HCSR04, I don't think. So what do? Well, we can make one, and that's exactly what we're going to do. We can go back down here to the main menu and then go to Symbol Editor so that we can edit or create a symbol. But first things first, we're going to need to add a new library, and we're going to make our own just for this project. And I guess we're going to name it symbol library. That's generally what I just like to do. I mean, you can name it whatever, like custom library or something like that. But yeah, here we go. So we're going to press this button up here to create a new symbol. And I'm just going to name it ultrasonic. Why not? The point of a symbol isn't necessarily to look nice, but it should be able to represent a component with the inputs and outputs. So I just went up here and added a rectangle, and I'm just gonna fill with background color. You don't need to do this, it just looks nicer like this. And then we go up here to add a pin. And as we've seen before, the pins on an ultrasonic sensor for VCC. That's the first pin. And then next one you might recognize as trig to trigger the ultrasonic sensor. And then we just do pin number 2. So we just go up in number. And the next would be echo. That will be the third pin. And I'm just doing this as I see it on the ultrasonic sensor. And that is literally it. So save all up here to save your ultrasonic sensor. And now if we go into here to load a symbol, when we search up our named ultrasonic sensor, you'll see ultrasonic right there. So we've just made that. Very nice. And now we can connect this. So I'm going to use a similar trick to this, the ground symbol. And I'm actually going to put in, so I'm going to search up 5V for a 5-volt symbol. Double click that to load it in. And we're going to connect that to the 5-volt output of the Arduino right here. And so that means if we connect this symbol right over here to VCC, which is what the VCC pin needs, then there will be an imaginary connection between these two. And then ground, same exact concept. Just gonna align it so that it looks nice. And you might say, okay, so now we could just connect this here to like pin 6 and then echo to pin 7. And well, actually they kind of intersected there. So this works nice, but we can do a similar thing with these symbols. We can actually do it for things that aren't power symbols. We can just use something called add label. So let me just add a label here. I'm gonna name it trig, and you can kind of guess where that's gonna go. It's gonna go to trig. I'm using X to rotate horizontally, just so that it kind of looks nice. And then we're gonna connect a wire to that symbol or that label right there. Control C and Control V to paste it. And I'm gonna copy this over here, and bam. D6 connects to trig symbol, and that trig symbol connects to this pin right here. And so now we don't need to draw an entire wire all the way across the schematic, or I guess across the Arduino. I'm gonna copy and paste this up here, and we're gonna rename it echo so that it would not confuse trig and echo connection together. And then we connect it here. Boom. Just like that. I'm gonna do the same exact thing, but without any of the symbols, and we're gonna see what it's gonna look like. Okay, so I finished. So without using any of the symbols, this is kind of what it looks like. While over here, we pretty much only had like one long wire. Everything else was very short and neat. So yeah, you can kind of see the difference between using symbols over here and using no symbols at all. We finished the schematic. Everything's connected how we want it to be. Now we go to the PCB editor. So it basically takes us to a place where we can make the actual physical PCB. Now let's load in the parts that we put into the schematic. Update PCB from schematic. Okay. Let's just update PCB. And you'll find that we only have one component. So what happened here? Well, when we loaded in the Arduino, it came with a footprint, which is essentially the physical layout of the component on the PCB board. Here, there is no footprint. And the symbol that we created, no footprint as well. So what do we have to do? Fortunately for the LED, we can select a pre-made footprint. Just search up LED. Depending on what LED you buy, it could be like a solder mount device or like a classic LED with a hole in it. So for now, we could just put in something like this. LED diameter with the 4mm diameter, 2 pins. A classic LED like that. Hopefully I'll put up a picture to represent what the real life version looks like. And you could kind of imagine how the wires would go into these pins right here. So we have that footprint. And so if we go into here and we update, we should have that. But this one, we're gonna have to make our own. So similar to creating a symbol on our own, we're gonna create our own footprint in footprint editor. Okay, so how do we start? Well, we also make a new library for a footprint, very similar to a symbol library. I'm gonna name this footprint library. Add a new footprint. It's going to be through hole because we need wires to go through some holes on the PCB. SMD would just be a pad, like a metal pad that's flat on that PCB, and then you could solder stuff to it. So we're gonna name this very simply ultrasonic. So okay, what do? Well, we add holes basically, and we have 4 pins, so we need 4 holes. But how far apart do these holes need to be? We could search up on the internet and see what the pin pitch of this sensor is. And it is 2.54 millimeters. So 2.54 millimeters apart. That's what pin pitch means. How far apart from the center of each pin do they have to be? And then the hole size. So I measured it with a dial caliper and it should be about 1 millimeter. So let's do that. And then the outside diameter. So the outer edge, let's make it 1.8, just so that it looks nice. So we have our individual pad shape, and now we could go up to here, which determines how far apart our snapping is. If we go like this, you could notice how smooth the movement is. But if we go to 2.54, every time you try and move, it'll snap to a position that is 2.54 millimeters apart, which is exactly what we need. So I'm going to copy this, and I'm going to paste it, put it right there. And obviously we don't have 4 pins with the pad number 1. So we're just going to do 2, 3, and 4. Now, what do these numbers represent? They represent the 1, 2, 3, and 4 right here. So we would know that pin 1 is VCC. So this would be helpful in real life when you're actually soldering it. You would want to put the names of each physical pin number right next to it. Or sorry, you would want to put the names right next to the physical pins like this. So 1, VCC matches up exactly with the schematic connection VCC here. Trig, echo, and ground. Okay. And then just to make it all nice, we're going to draw a rectangle around it so that we know where to put our sensor, I guess, so that it's more obvious. We save it just like everything else. And now we could go into here, go into our footprint, and load in ultrasonic, just like that. So you can kind of see how pad number 1 is VCC. It's labeled there. And that represents these connections here, VCC, trig, echo, and ground. And now we update the PCB. And there it is. All right. So now we connect everything together. So I'm just pressing R to rotate here. So what we would do is use this here, route tracks, or the letter X. You can press X for this. Well, first you press X on something like this pin here. And then you essentially just follow whatever the computer or the CAD software is telling you, which is fine because this is what you've defined in here, right? So trig, we want it to connect to pin 9. So trig connects to pin 9, which is trig. So you can connect it all like this, but there's, again, a better way of doing all this. So before we do all that, we can actually draw a rectangle. So why would we want to do this? Well, this rectangle will represent the PCB board, the edge of the PCB board. And how do we define the edge of that? Well, we can double click it, go to layer, and edge cuts. So this is going to define the edge of the PCB. So if I go into the 3D viewer, you're going to see that this PCB right here is the edge of what we have drawn right here. Let's just go back here. I guess make it all nice. If you want to align 2 things together, you can control click them to select multiple. And then you can do align and distribute. So if you align horizontal to center, they're going to be kind of vertically aligned. You may or may not want this, but for now we don't need it. Let's try and make the PCB as small as possible. And now this PCB is very compact. So now we're going to add a filled zone. And what this will do is it's going to create, well, a zone. Of what though? So PCBs generally have multiple layers, and generally we would use one layer. So like FCU stands for the front copper layer. This means that for the first layer, we can make this all connected to anything that needs to be connected to 5 volts. So I'm just going to do this real quick. You can select that and select the corners of your PCB because the zone needs to be across the entire PCB. And then we're going to do the same thing, but now on the back side of the PCB, the second layer in this case, we're going to make it a ground layer, which we call a ground plane because it's a flat surface and it's meant for ground. So we go here, again, make the zone the size of your PCB, and notice VCC and ground on all of these components. So the ground connections and stuff like that. And we press B, press the letter B, and it will fill in your zone. And you will notice that now VCC is connected to this red connection here, and then ground is blue. So we've essentially covered the entire top plane, the top layer, with metal, and it will connect anything that needs to be connected to 5 volts. So it kind of does the connections for us, which is cool. It's pretty nice and easy, especially when you have like tens of components on your board. And now that means we only need to connect the non-power signals. And it's literally just 3 individual wires. And we press B again so that it can make space for those wires. It's now showing a wire or like a connection that needs to be made here because we've kind of blocked it out. So I'm gonna click and drag that over here and hopefully we're good. Okay. So if we go here, we can kind of see how now, before it used to be plain, but now we see an actual like PCB trace. And yeah, that's basically how you would make a PCB. One of the last things you could do is design rules checker. So you go up here, run design rule check, and that will essentially check everything for you. Like if you've missed anything, if you have unconnected items, in this case, we're all good. Okay, so we have the PCB, but only a virtual model of it. So how do we get from there to a real PCB? We can send the PCB files to a PCB manufacturer like PCBWay, the sponsor of this video. For KiCAD, there's actually this nice plugin that you can get from PCBWay that, when used, will automatically send your Gerber files related to your PCB design, basically, to PCBWay. So no need to generate the files yourself and then drag them onto the website. It's not that hard to do, but the plugin makes it much more convenient. You can get this plugin by searching PCBWay plugin in the plugin tab and downloading it. After that, you should have the button to send in your PCB on the PCB design page. Once your PCB is sent in, you can specify different parameters, like the number of layers you have. In this guide, we used a default of 2 layers. To keep things simple, the default settings would work for most basic PCB designs. To the right, you'll be able to see the estimated costs and shipping times. From there, you can send in the order once you're happy with the parameters. And then PCBWay will check the PCB for any errors. After it's approved, you would order the board just like you would order anything else online. Finally, you'd get your PCBWay PCB about 1 week after your order. Alright, so back to the video. So you got the PCB, but it has no components on it. How do you get electronic components in the first place anyway? Well, some of them actually come from Amazon, like the HC-SR04 ultrasonic sensor. However, more general electronic components, like anything that is a chip or a basic electronic component like a resistor, would come from electronics vendors. I like to use DigiKey, but others exist, like Mouser. On those sites, you can search for electronic components by category, then filter by characteristics to get the part that fits your project's requirements. You then add the components to your cart and check out like you would with any online store. Alright, so we know how to apply the PCB design process to a basic example, but let's see how it applies to a more advanced example, like an object-avoiding robot. Normally in engineering, we determine the requirements for a project so we can get a desired result. For this robot, the requirements are that we need to be able to detect objects somehow, and then be able to move out of the way of that object using some actuator or motor. We then need something that coordinates all of those actions together. So, the PCB of the robot would include an Arduino Nano, which would take in inputs from 3 ultrasonic sensors so that we can detect objects using distance values. And then the Arduino would use that information to spin 4 motors, each with 1 wheel, to move out of the way. To power these motors, we then use an H-bridge chip, which would deliver the required current and voltage to the motors, based on a signal from the Arduino. Alright, let's dive into the design. So this is the schematic of the object-avoiding robot example. And as you can see, there's actually not too much going on here. And again, you can see here we're using the labels, custom and pre-made, so to speak. And we have this right here, VDC, which is a new symbol that you probably haven't seen before. And that just represents a positive direct current power supply. Basically, if you were to connect this to a battery, you would use like a VDC as just like a positive voltage marker. But essentially, we would just use this to indicate any positive voltage. For example, that connects to a battery. All right, so that goes into the Arduino and it powers it because remember, we can't use a USB to power this Arduino Nano here because these require a bit more power. And this is a motor driver integrated circuit, a chip that we've seen before in a previous video, and that's responsible for powering these 4 motors. And we're using each one of these outputs on each side to power 2 motors. And these motors are on one side, this case, the left side of the robot, and over here, the right side. And these labels here, they connect to the outputs of the Arduino Nano, and that allows us to control this motor driver chip so that we can control these motors and power them. And then we have the recognizable trig and echo labels to control these ultrasonic sensors. The left, mid, and right ultrasonic, essentially meant to detect objects on the left or in front of it or to the right of itself. So that's basically the basic rundown, basically breaking it up into a power source, and we would solder battery wires to these pads. And then we have the sensors, which go to the Arduino, and then we use that information to produce outputs that go to the motor driver, which powers these motors in the fashion that we want, that we programmed. So to put this all together, in real life, the PCB sort of looks like this. And I added some physical 3D models that I downloaded online to make this look pretty realistic and nice. And so let's go into here. So basically, I made a curvy edge cut, which, I mean, you could do if you want to, or you could just make a square, which is fine. But in this case, you would want an angled side right here for the object avoiding robot so that you can actually make it point to the right or point to the left to detect stuff. So that's a bit of a special kind of work there. You would have to use the draw line tool to draw something diagonally, and then you can define that as a edge cut. And then just make sure that you connect the vertices together. And so yeah, I place the components down inside of this cutout, and these are holes. You would find it over in the Add Footprint tab, and you could search up just hole or mounting hole. These holes have a specified diameter. So if you're using a screw of like 5 millimeters, you can go down here and select 5.3 millimeters so that it fits an M5 metric screw, or metric bolt, sorry. And then we have these on my footprint of the ultrasonic sensor. I added a pretty big box that indicates, one, which direction the sensors should point in, just to be sure of myself, and also the box that the sensor would occupy. And then after that, I fill in with these fill zones over here so that I can get the ground and the power planes, and then I just connect them all together. And then I just have the traces go between all the necessary components, which I've defined over here already. And so you can kind of see how the basic example from before with the just one ultrasonic and one LED can apply to something like this. And then this is a little new. So this sort of represents this right here. And so we would be able to take two wires, a positive wire from the battery pack, for example, and then a negative wire, and then we melt metal onto these, essentially bonding them together so that positive can go into here and power everything else, and the negative wire can be bonded to that and have everything return to the battery in a closed loop. That's pretty much it. So I already ordered the PCB using PCBWay, and I also already ordered the electronic components that I would put on that PCB. So how do we put those two things together? We do something called soldering, which is taking something called a solder composed of metal and melting it between metal contacts of the PCB and contacts of the component to bridge those two together, making an electrical connection. By the way, you can get a soldering iron on Amazon. Any of them should work, and just make sure to get some solder along with it. Alright, now we can take this PCB and put it onto a chassis, which was covered in the 3D modeling with CAD guide. Align the holes there. Alright. Okay, that's on. Okay, so theoretically, if I turn this on and I kind of do this, okay, that's good. Essentially, this board is being told to drive all of the motors in a forward direction, or like the command given to this robot is to drive forward. Now we experiment with way we should solder these wires, because you can't really know for sure which way to solder. Here it seems like we gotta do that. Okay, So now we should be able to turn it all on and have that horrible sound play again. Here are the wheels. Let's try and put these on, press them in like that. What we can do is we could probably add something that has some friction right here that prevents it from sliding out like that. Maybe some rubber tape or something like that. Must be something like this, probably. Oh yeah. Yeah, now it's not going anywhere. That's a great idea. There we go. Looks quite nice, quite close to the CAD model. Now we have a fully assembled robot, but it actually doesn't do anything until we program it. That will be covered in the next video. In the description, I've linked the files and the parts for the object avoiding robot if you want to check it out and learn from it that way. All right, so I only talked over the PCB design of the object avoiding robot back there, but would you guys actually like a more, I guess, step-by-step guide of how I went through it, or like, I guess I remake it again and you guys kind of just see how I remake it? I don't know, just let me know in the comments. I'll be releasing the next videos of this series every few days or so keep an eye out. If you want to learn about programming the robot and in general, any DIY project using Arduino, then click on the video on the screen once it releases.